All right, maybe let's begin. I was asked whether I would mind if you sell popcorn or chips before we start with the lecture. I wouldn't mind. Just give me a share of the sales. But this reminded me also of the albatross sketch by Monty Python. Do you know that? If not, that's part of the homework for next week. Look it up on Google. Good. I told you last time that our main purpose, essentially for the whole lecture, is how to calculate correlation functions. And this reminded me of the fact, and that is an embarrassing omission, that we started the lecture on cosmic structure formation without ever clarifying what structure should be. So I need to specify this. Structure is the presence of correlation. That's it. And so this is one possible definition of structure, of course, right? But this is the definition that I want to adhere to. Structure is the presence of correlation. And therefore, if we speak about cosmic structures, we need to speak about how to quantify structures, and this is why our correlation functions. This is our main purpose. So we made a rather big step forward last time to actually getting to calculate correlation functions of arbitrary order. In the beginning, from a free generating functional. And with a free generating functional, I meant one generating functional that does not contain any particle interactions yet. And this was the reason for the long sequence of statements in the beginning of the lecture about how we can choose particle trajectories such that the fiducial trajectories themselves do already contain as much gravity as possible, and to reduce the contribution from particle interactions on the particle trajectory. But of course, later we will have to introduce what happens if the particles in fact do interact. But for now, we are dealing with a free generating functional, and this is for the moment interesting enough. All right, then I told you last time that we arrive at correlation functions for the density by applying as many density operators as the order of the correlation function should be to the free generating functional. And we saw the following. Particle densities are given by distributions, delta distributions. The sum over delta distributions is the sum over particle positions, particle densities, one at each particle, one delta distribution at each particle position. We can't handle these delta distributions analytically very well, so we transform them into Fourier space. Then they get Fourier phase factors. These Fourier phase factors contain particle positions, and the particle positions are being replaced by suitable functional derivatives of the generating functional with respect to the source field J that appeared in the free generating function. So then we arrive at differential operators appearing in exponential functions, and I wanted to make sure to you that derivatives that appear in an exponential are shifts, right? Are spatial translations. And so we arrived at expressions like this. And then if I apply a sequence of density operators, R of them, and I realize that R is not a good character for this purpose, but I didn't have time to change it everywhere in the lecture notes. This is what we did, right? This was simply the free generating function evaluated at a shift tensor. This was the main result of last time, right? You apply as many density operators as you need to for the purpose you have in mind, and you arrive at the free generating functional evaluated at a shift operator, right? Because part of this operation here is that you set the source feed to 0 once you're done, not before. All right, that was it. Good. Then we could make some progress. I told the story about the chips and the popcorn already. Enjoy your food. I do. Thank you. Okay. So we need to evaluate these things, and we said this is an integral over the initial phase space distribution times this phase factor here, where now for x bar we need to insert x bar 0, which is the part of the trajectory that does not contain any particle interactions yet. All right, so far so good. And then the following happened. I was really wondering, did I say all of this last time without you falling asleep? It's amazing. Now we insert the initial probability distribution here, and we saw that this is a simple Gaussian under certain assumptions, and that we have to, sooner or later, we have to lift them. But under certain assumptions, this initial phase space distribution is just a Gaussian in the momenta. And then we could split up this scalar product here, and we could carry out the momentum integration. And we did one more thing. That was, we picked one of our n particles and chose it as the center of our coordinate system, and then referred all the other coordinate positions to that. And since nothing in our calculation may depend or must depend on absolute particle position, right? Because we have a homogeneous random field, we can integrate out the origin of our coordinate system. And the result of all of that, lengthy, was that we can write this generating functional as 2 pi q. Now a delta function over all wave vectors that occur in these R density operators here. This is the consequence of having integrated out one of the particle coordinates. Then we have rho bar to the power of R. That's the mean particle density to raise to the power of the number of density operators applied. And then we have an integral left over all relative coordinates. And this looks like e to the power of -1/2 LP P CPP LP plus I LQ times Q. All right. And the LPs were minus sum over PI KI and the LQs were minus the sums over KI for all the particles involved in the density operator. That was the main result of last time. Yes. That should be IR. Yes. Thank you. All right. That was about the end of last lecture. I went one step further and said, since we know what the CPPs are, we can evaluate this further and say LPT times CPP times LP. This is sigma 1 squared over 3 times LP squared plus TI PJ KI transpose CPI PJ. it's just inserting the definition of these correlations here. Then we have a contribution from equal indices between of this LP tensor and this LP tensor here. This gives you this contribution here from this moment, sigma 1 square of the power spectrum. And then we have the cross terms, right, of all particle pairs with different indices. And now we can go one step further and use the knowledge that we have about the CPIPJs here and write this is sigma 1 square divided by 3 LP square minus. Now let me assume that we are calculating all synchronous correlation functions. In other words, these density operators all act at the same time. In other words, we are fixing a time slice through our model universe and calculate density correlations on this time slice. This doesn't need to be. And there could be good reasons for calculating asynchronous correlation functions, right? If you want to correlate density fluctuations at different times. Because, for example, you observe two cosmological objects that are at different distance, therefore emit their light at different times, and you want to calculate asynchronous correlation functions. Could also be. Let's neglect this for now and write. Then, of course, all these times are equal, and we call them just T1 squared. Now we have Ki. Ki, Kj, that's just the scalar product of these two wave vectors here. Now times A1. It's the A1 correlation function we defined some time ago. This must be now evaluated at the distance between particle I and J. Then we have plus Ki times the parallel projector between particles I and J. In other words, that's the parallel projector here relative to the axis connecting particles I and J. All right, so we got this expression, and this is essentially the most convenient version of the result that we can have. Do you have questions up to this point? Yes. Thank you. Yes. I don't know whether you remember these functions A1 and A2. For the moment, they don't matter very much. They are integrals over the power spectrum times Bessel functions. So A1 was the integral over the density fluctuation power spectrum times Bessel function of order 1, spherical Bessel function of order 1 divided by its argument. And A2 was the same integral with the Bessel function J2. Not so important for the moment. All right. So let's have a look at an example now. And the example is going to be simple, because of course I want to save the difficult examples for you to do in the problem sheet. So let's assume R equals 2. So we want to calculate what is usually called the power spectrum, and a 2-point function in Fourier space. So then this delta function out front tells us right away that K2 must be the negative of K1. So essentially we have one wave number only. And this simplifies, of course, the whole rest a lot. And then, of course, since I and J can only run through 1 and 2, and in the last term here I must be different from J, there's just a single copy of I and J that appears here, namely the pair 1, 2 or 2, 1. Okay. So we have K1 equals minus K2, or let's do this the other way around. And then I want to introduce the angle between K1 and the connection between particles 1 and 2, which is my single relative coordinate. So I don't need to give it any indices now. So this angle, or rather the cosine of this angle, is mu. So I have a single angle that appears there, and I call this mu. Okay, with this equipment, yes, and I know that LP is now minus T1 K1 for particle E1, and it would be minus T1 K2 for particle E2, but K2 is minus K1. So this is LP, and LQ is the same thing without the T factor, without the time. So LQ is minus K1, E1 minus E2. Aha. Okay. So then, if I go through these terms that we have for LP multiplied with CPP multiplied with LP, LP squared is just T1 squared times K1 squared plus K2 squared. But K1 squared is K2 squared, so this is just 2 times T1 squared times K1 squared. Okay, now for the others, I now need, of course, to take index pairs 1, 2 and 2, 1 into account. I need to sum over them, so I get twice the same contribution. So this means that the whole thing is going to be 2 over 3 times sigma 1 square T1 square K1 square. This is this term here. This gives rise to a lot of headache. Then here I'm getting products of different k's. They have a negative sign. So this turns this negative sign into a plus. So I get plus T1 square A1 K1 square. And then I have K1 square U square A2. And we are done. And let me perhaps explain this last term in a bit more detail. Now, of course, I have a single parallel projector here because there's only one connecting line between particles 1 and 2 left. So this projector looks like this. So this means that K1 times the parallel projector times K2 is K1 times R hat if I multiply this vector to this matrix here times K2 times R hat. But K2 times R hat is minus K1 times R hat. So I get this. And by the way, how we introduce the angle between R and K, this is minus K1 times mu. And this appears squared upstairs, and we're done. Yes? Thank you. Yes? Okay, and now we can write down this free power spectrum. And it's going to reappear very frequently. And this is one of the main reasons for calculating it here. All right. This is now just a summary of what is left above. We'll set 0 of L for r equals 2. That was our goal. This is now 2 pi cubed delta d k1 plus k2 as a consequence of homogeneity. Then we have rho bar squared. And then we have an integral over the one three-dimensional leftover relative coordinate between particles 1 and 2 of the exponential of minus sigma 1 squared over 3 times k1 squared t1 squared. This does not depend on r anymore, obviously. Then we have minus t1 squared k1 squared a1 plus mu squared a2. And then, of course, we have the remaining Fourier phase factor. I can write in this way. This is beautiful. This is a nonlinear power spectrum, analytically calculated, for a free particle system, of course, but it's a nonlinear analytic power spectrum. All right. Of course, now you want to confirm certain properties of this power spectrum, and I asked you to do so on the last problem sheet. In cosmology, these functions a1 and a2, or the maximum amplitudes of these functions, are very small. They are numbers on the order of 10 to the minus 4. So this means that in the beginning with a capital B, right, the beginning of the universe, in the beginning, this is a small number here. And T1 is even 0 in the beginning. Wait a moment. Anyway, at early times, this is small. Even for large wave numbers k, this is a small number. And then, of course, you can linearize this exponential here and write this exponential as 1 minus t1 squared k1 squared times these a1, a2 functions here. There's also this prefactor here, which you can then handle in a simple way. But nonetheless, if you then integrate this linearized exponential together with the Fourier phase factor, you get the linearly evolving power spectrum back, and this was the main point of the last problem sheet. Right, to reconfirm that this expression here at early times reflects what you expect. At late times, at large wave numbers, this is an awful integral for the following reason. It oscillates like hell. At late times here, at late times, of course, these become large numbers here, these T1 squares here. And then if you go to large wave numbers, that is to small scale structures here, then the amplitude of this exponential expression is getting very large. So you have to integrate over a quantity that goes like this. And this is a nightmare for any computer to solve. Yes? Indeed, you can. But we are getting to this later. Don't rush. Okay. So this is the first thing I wanted to say. It reproduces the linear limit. Well, almost. Almost. Actually, you would expect that if you set T1 to 0, then the whole thing should be the initial power spectrum. But obviously it isn't. Right? If you drive the limit T1 to 0, then this exponential is just 1. You integrate over this, you get a delta distribution rather than the original power spectrum. Why is that? This looks like a bad mistake, doesn't it? This is because we neglected density correlations in the beginning. Right? Remember this d hat operator that we introduced? We set d hat 1, and this meant that we neglected density fluctuation, correlated density fluctuations. In the beginning, we just said densities are equally distributed in space, or they have a flat distribution. Particles have a flat distribution. We just take momentum correlations into account. Well, if you do that, then the initial power spectrum, of course, doesn't show any structure. Structure would only emerge once you let the particles run for a while, right? Because then through the momentum correlation, structures would form. So at early times, our approximation failed. Our approximation of d hat equals unity. So we need to see what happens if we fix that. All right. Yeah. We do what? Yeah. What we mean by that is that we look at volumes such that the third root of this volume is very much larger than any correlation length that is represented in the original power spectrum. Okay, so yes. Perfectly right. So we are assuming that this volume here, or that its cube root is so large that wherever you arrive in your integral towards infinity, the integrand is already cut off by the correlation function. That's in fact the main point. But this is the essential assumption, right? You cut out a subvolume of the universe, which is very much larger than the largest structures that it hosts. What kind of power spectrum is this? So we had before delta, P delta. So remember that A1 of Q was 1 over 2 pi squared integral over dk P delta of K1 KQ divided by KQ. Right, so it's the density fluctuation power spectrum that matters here. Right, we are looking at density structures in the density field, and therefore we have to compare this to the correlation length in the density fluctuation, which is of order of U10 megaparsec. And this will typically be of order the observable universe, 3 gigaparsec. Yes. A1 is negative. Sorry. No, it isn't. But for any computer that has to do this, there are values of this integrand in between where the argument gets extremely large. Yes. It's the linear power spectrum. That's the linear power spectrum of the initial condition. Otherwise, we would have nice consistency equations. All right. So far, so good. Now, usually it is a good idea to not use this expression in this way, but to do something else. First of all, it is convenient to factor out this Gaussian that does not depend on the radius anymore, right? Because this is just a constant factor for the integral. So then you have this Gaussian prefactor here. And then you have the remaining integral of this thing. And now I'm introducing something that makes at least the integration of this quantity here much more easy to handle for a computer. I subtract 1. I stop here. And then, of course, I have to fix what remains. But what remains is a delta distribution at K1. So you can easily split off a delta distribution, right? Because this integral over R over this Fourier phase is just a delta distribution. So I subtract it first and then I add it again. The integral ends here. Okay, you look puzzled. Anyway, so this delta distribution at K1 equals 0. This is a contribution to the power spectrum at wave number 0. But the Fourier transform of a delta distribution at wave number 0 is just a constant in space. This is not what we call structure, right? It's just that would just be a constant distribution or a constant contribution. So usually we can just ignore this delta distribution here, and then this integral, here takes the role of the non-linearly evolved free power spectrum. Right? So we neglect this prefactor of rho bar square in the delta function because that is usually not part of the definition of the power spectrum, and this is what we call curly P of K1 and T1 and so on. So whenever you see this curly P appearing here, this is what I mean with this non-linear evolved free power spectrum. And it will appear quite a number of times. Okay. So far, so good. This thing is awkward. This means that structures are first going to form, and then they are going to disappear, right? Because they will be suppressed by this Gaussian prefactor. And that is exactly what happens, right? We do not consider particle interactions now. Particles are just freely streaming. Their momenta are correlated. There are sections in space where the momenta are converging. There are sections in space where the momenta are diverging. If you look at the section of space where the momenta are converging, they do this, and structures form, right? Particles get compressed. They end up in ever smaller volume by the converging momenta. And once they are through with that, they move past each other again. And so unless we switch on gravity, this exponential factor describes, or seems to describe, the decay of structures after they have formed. For the moment, this is inevitable. I'm saying that this seems to describe the decay of the structures because it's not quite true. Interestingly, it turns out if you make an asymptotic analysis by means of the saddle point approximation, then you find out that this exponential factor is cancelled exactly. And the power spectrum does not decay exponentially, but according to a power law. Right? So this exponential prefactor here is extremely misleading. And it's only in the past 2 years or so that we found out this is not exponential damping. Because if you take this together with the asymptotic behavior of the curly P, then it is not exponentially decaying, but algebraically. All right, maybe this is enough for the curly P, unless you have questions. Now I think we should have a look at this, at what we did when we set the d hat operator to 1. Right? Because it is an annoying feature that if you set t1 to 0, the whole structure is gone, even though you start with imposing structure on the initial time slide. All right, so let's go to that. But first of all, there's an intermission. All right, let's go back and see what this d hat operator would do. And I didn't do this in the beginning because then you get just awkward expressions and nobody sees through them. But now I want to show what happens with the d hat operator if you do not set it to 1 for a density fluctuation power spectrum, right, for r equals 2. Because then it's much easier to track, and we see what happens. All right. Remember, everything started with a probability distribution in evolved phase space. And this probability distribution contains some prefactors. And then there was an integral over the Fourier conjugate variable Tp that was Fourier conjugate to the momenta. Remember how we calculated this? We went into we went on the initial time slice where we set our initial conditions. We imposed the Gaussian distribution for all our variables, right, the density fluctuations and the momenta. And then we introduced some conditional probabilities and so forth. And then studied the probability distribution of our particles in this initial phase space in terms of the characteristic function of that probability distribution. And so we arrived at this characteristic function. Very unfortunate that now the R has a completely different meaning. I'm sorry for that. And then we needed to transform back into back from Fourier space. And this characteristic function here looked like this. Exponential of minus a half. Now, TP transposed CPP TP. That was the probability distribution for the TPs here. Then minus a half R transposed C delta delta times R. And then minus R transposed C delta P times P. And then when we went through this calculation for the first time, we said, okay, we will later have good reasons to neglect the hat operator completely, which means that we could set R to 0 right away. Then all of this was gone, and we retained only a Gaussian distribution in the moment. That was the logic at that time. And the R's here are just an auxiliary variable introduced for us to take derivatives. Right? The d hat operator was this kind of thing. Originally, there were n factors to the d hat operator, but this just took derivatives with respect to with respect to components of this variable R. So I'm just tracing our steps back to a moment where just before the R's disappeared, and I'm now leaving the R's in and see what happens. Okay. Now we have to take an integral over Tp, right, in order to return from Fourier space. When we set R to 0, Tp, okay. When we set R to 0, these two contributions were gone, and we just had to Fourier transform a Gaussian, which led to a Gaussian, and we were done. Now, we will have to integrate over a Gaussian, and we will be done. So there are now these prefactors. Then we have an integral over Tp. Now let me insert this exponential here. Momentum correlations. We have the density correlations, and we have the cross terms, right? The cross correlations between density and momenta. And we have the Fourier phase factor here. So this is the integral we now have to solve. And it's in fact very easy. You see, we have to integrate over Tp again. But this Tp appears in the Fourier phase here as a scalar product with some vector. I write this as this. That. Now I want to have this factor of I in front. So I'm writing plus I. Now P. Okay, this minus sign is an I squared. So I get plus I times R transpose C delta P. Now, of course, this expression containing only r's and no TPs can just be pulled out of the integral. And what remains is a Gaussian Fourier transformed with this piece here acting as a wave vector. So of course we get a Gaussian back. Sorry. All right. So these are all the prefactors we would have. Then I'm pulling exponential of minus a half r transpose c delta delta r out of the integral. Then I get this. We have very young students here. Then we have this Fourier transform of the Gaussian, and it's going to be a Gaussian. So that's going to be exponential of minus a half p plus I r transpose c delta p transpose times cpp to the power of minus 1 times p plus I r transpose c delta p. And that is it, right? If you have difficulties with this step, this is just our new wave vector. All right, we have factored this out. We have a Gaussian. This is our new wave vector. We get a Gaussian with inverse correlation matrix, where the new wave vector takes the role of the previous variable, right? So this is the result we get. Okay, that was easy. Now, in fact, we have a new prefactor here, but I just don't care about this. Now, see what happens. We now get an additional contribution that is squared in the r's here, that we can add to this one here. So we must get something like exponential of minus a half RT times a new matrix B that we have to specify times R, where I have swallowed this contribution together with this times that times that. Aha. You see, here we have a factor of I, here we have a factor of I gives you a minus sign together with this. Well, so B will be the original C delta delta, now minus something. And this minus something is C delta P times CPP to the minus 1 times CP delta. All right. Okay. Then, of course, we have the Gaussian. The Gaussian in the momenta that we already know, right? This was the original contribution that we had before. And then we have 2 times the same contribution, right? We have I times R times C delta P times CPP to the minus 1 times P. And we get this twice, right? Because this covariance matrix here is symmetric. So we get minus a half, now 2 times this contribution, the I remains, and we have R transpose C delta P CPP to the power of -1 times P. And you see how these cross correlations between density and momenta and between densities now enter into the game if we do not neglect the R factors right away. All right. This is the probability distribution for the particles in phase space. Now remember, the next step was that in our generating functional, once we had density operators applied, we integrated out all the momenta. And now of course we can do exactly the same thing. So now I'm going to take this exponential factor here that contains only momenta, and I integrate over the momenta, as we have to do in our generating functional. So now I'm doing this. I'm integrating over P, exponential of -1/2 P transpose CPP to the -1 times P minus I times R transpose C delta P CPP to the -1 times P. And then in our generating functional, we also had a Fourier phase, which was this LPP. I'm just tracing steps back that we had done previously, setting all the R's to 0, but now with the R's included. So I'm being really schematic here. Now you see, again, we have to integrate over all momenta, which is of course again a Fourier transform of a Gaussian. Now I have to combine these two vector, or these two scalar products with the momentum into one new wave vector here. They both have a factor of I in front. So let me replace this here directly. By plus I. Now, of course, we have LP first. And then minus R transpose C delta P CPP to the -1. This is our new wave vector times P. And again, we just do a Gaussian integral, which does the same thing as always, right? It replaces the independent variable now, the P, by this wave vector here. And it again inverts the inverted CPP. And by the way, part of our normalization factor that we would have to have taken into account is cancelled in the next step. So miraculously, the result is not just sketchy but almost correct. Are you here? This should be CP delta times R. That's true. But if you return to this version of the matrix B, then it's correct. Yeah, same thing happens again. Yeah. Nonetheless, the result will be so simple, right? That I'm doing it right in the lecture now. But you're right about this comment, right? I'm mixing column and row vectors here accidentally. You know, these indices tell me what you have to do. But since I wanted to use this calculation just to show you what additional terms we will get in the power spectrum, this should be sufficient. So this integral here is again, right, a Gaussian. Now with, no, I'm setting it right. Now we get CPP to the -1, CP delta times R. Now the whole thing transposed. Now CPP, right, because instead of CPP to the power of -1, after the Fourier integral over the Gaussian, we get CPP restored. And then we have LP minus CPP to the -1, CP delta times R. Uh-huh. And you recognize part of what we already had, namely this one. Well, good. this is going to show up again. Then we get an additional contribution of the sort R transpose times matrix times R transpose. Let's have a look at that. So I'm now exclusively looking at this factor times that factor here, because we have already this thing out front that we have to combine it with. So we get an exponential of -1/2. Now these two minus signs combine to a plus sign. Then we have R transpose C delta P, CPP to the -1, CPP to the +1, CPP to the -1, CP delta times R. Well, look how lovely this is. Any pair of these annihilate themselves. No, annihilate each other. So what remains is, as the matrix in between the RT and the R, is a C delta P times a CPP, no, CPP to the -1 times CP delta. And it comes with a positive sign in comparison to this one. So this just means this is going to restore C delta delta instead of B, and nothing else is going to happen. So this term is doomed. This is gone. Okay. What else? Well, then, of course, we get a double copy of the mixed term. The mixed terms get a negative sign. Together with this negative sign is going to be plus. The 2 is going to cancel. So in addition, we get a factor of exponential plus 1 times, now this one here, R transpose C delta P, CPP to the -1, I'm here, right? I'm multiplying this with CPP. And I'm multiplying this with LP. And now we have everything together. And you see, together with this prefactor that we already encountered here, which has a negative matrix product like this, we only retain a factor containing C delta delta. we retain a factor containing C delta P. That's this one where CPP to the minus 1 meets CPP and goes away. And we get our original momentum correlation. All right. So the result of the lengthy consideration is that I need to clean the board. Oh yes, the break. You wanted to have a break. Let's have a break. Let's break for 5 minutes. Okay. So what do you think? Should we should we restart? Long enough? All right. So the whole calculation had the following purpose. Our expression for the free generating functional after applying a sequence of R density operators. R, I know. Which used to be some normalization factor times an integral over R. Oh. So let me call this integral over Q. Which looked like this. Looked in the past. Is going to change. Have the same normalization factor. And now exponential of minus a half R transpose C delta delta times R minus 1/2 LP transpose CPP LP plus R transpose C delta P times P, LP plus I LQ times Q. This is what happens if we do not neglect the R contributions before. But now we have to apply the D hat operator. Okay. And now you see the following. Suppose you have a 2-point function. Suppose you want to calculate a 2-point function. Then this D hat operator is just this product of derivatives here. And the R here only contains 2 contributions, right? One for each particle. Now what happens is the following. First of all, you get a 1. What happens with this, you already know. Right? This was the whole point so far. So this then gives you the power spectrum that you already know. But now we get additional contribution. We get an additional contribution by the combination of single derivatives. And remember that once we are done with this, we need to set R to 0. Now, if I apply a single derivative with respect to R to this exponential here, I do get, of course, the same exponential. I do get one contribution that remains linear in R. And I do get one contribution that does not contain R anymore. And then I set R to 0. And this is gone. And only this term remains. And the exponential shrinks to what we had before. So this introduces the first derivatives here. These restore the density momentum correlation. So this restores that where you have an overdensity, you have a convergent convergent matter flow. Now, if you take the combination of derivatives here, you do a second derivative of this thing, and then you set R to 0. So you do a first derivative, you retain this as the only contribution that still contains an R. You do this again, this restores the delta-delta correlation. So this is the way how you restore the initial density correlations, and then the result that remains does not vanish for time to 0. It does retain the density correlations at time equals 0, and it is valid for all times from 0 to very large. And I'm not going to fill in the details because you should do this. All right. So this explains how you restore these additional correlations. Now, this also shows why at late times we can neglect this term and that term in comparison to that term. You see, this is growing like time squared. The LP factors contain a time each. So this grows like time squared, this grows like time, this grows like nothing. At late times in cosmology, by the choice of our time coordinate, the time grows to approximately 1,000. Right? So very quickly, this becomes very much larger than that one. And even larger than that one. So this was the reason why we could neglect anything else but d hat equals 1 if we look at late times. Right? It becomes immediately obvious that this can't be wrong, this can't be true at early times. And now you see why, right? Just because this term grows so much faster than that one and that one. If you work this out, and by the way, this was a bachelor thesis in our group, if you work this out, you see that for approximately the first 5 to 10% of the cosmic evolution, these terms do matter. They don't matter much even then, but these terms matter, and afterwards they do not. Okay? Good. Do you have any questions about this? Then I have questions for you on the problem, please. Good. Now I wanted to show you something that may look completely awkward at the first place. I have an ideal gas in mind. Not to say that I have an ideal gas in my head. This is not quite correct, but I have an ideal gas in mind. The reason why it is so simple to deal with ideal gases in thermodynamics is that you can factorize the generating functional, or rather the partition sum. And whenever you have a physical system where you can factorize the partition sum, this is like Christmas, right? This is wonderful. Can we factorize our generating functional? At first sight, it looks like no, but let's have a look. So what is this like? Let's again look at the generating functional after applying a sequence of density operators already. And I'm going to write it down again, neglecting the normalization factor. So we have some normalization, then we have, we'll use R as relative coordinates again. Then we return to the usual way, right? We are late in not today, but we are late in cosmic history. And so I'm neglecting the C delta delta and C delta P contributions again. Okay, now what do we have? First of all, we have applied a sequence of R density operators. It's getting too awkward. Let's call it N density operator. Then these R's here are L minus 1 relative coordinates. So there are L minus 1 relative coordinates. But this covariance matrix here contains all pairs of relative particle coordinates. And these are, of course, very many more. So suppose I introduce coordinate differences between all particle pairs. I call them RJK, coordinate difference between particle J and K. Well, they are, of course, I can construct them, of course, from the previous one. But if I look at the number of these coordinate pairs, then of course that's L minus 1 divided by 2. It looks like I have no chance to factorize this, right? Because this covariance matrix here contains extremely many, well, not necessarily extremely many, but contains many more relative coordinates than this phase factor does. All right, but let's suppose that we artificially introduce new coordinates, RJK, and integrate over all of them here. In other words, I want to expand the space over which I'm integrating by a huge number. And I want to transform this here to an integral over all coordinate pairs, because only then I will have a chance to factorize this. Then how many new coordinates do I need? I want to have L times L minus 1 divided by 2. I do have these. So I need L minus 2 times L minus 1 divided by 2 new coordinates. Well, okay, if I have a power spectrum in mind, right, L equals 2, I'm well off. But of course, if I look at, there's a reason for doing that. If I look at power spectra or correlation functions of very high order, then I need very many additional coordinates. So, this means that I want to change this integration over all R to an integration over all relative coordinates. Well, then first of all, I have to copy what I already have. But then, of course, I have to introduce delta functions that make sure that the new coordinates satisfy this condition here. And how many of these delta functions do I need? Well, so many. Let me explain what product over A larger B means, but I need new delta functions, right? I need to make sure that all my new coordinates are related to the old one. Okay, now this index B here runs from 2 to L minus 1. And the index A runs from B plus 1 to L. So in total, the index combination AB runs over these L minus 2 times L minus 1 divided by 2 combinations. So these are my new coordinates, and these delta functions there are just there for binding them together. Okay, now I have artificially blown up my integration space. Now, in order to make this even more awkward, I'm now going to introduce Fourier representations for all these delta functions. All right. So for each of these delta functions, I'm doing the following thing. Of course, for each of them, I need to introduce a new wave number. And all these new wave numbers, L minus 2 times L minus 1 divided by 2 of them, I introduce a KAB prime. Right? All these new wave numbers get a prime. And then I write this delta function as I times KAB prime RAB minus RA1 plus RB1. And if I now introduce all of these delta functions, I get one long Fourier phase that contains all these new wave vectors here. So then at 0 of L, the normalization factor. Now I'm integrating over the whole set of relative particle coordinates. The Gaussian part. Then I have relative particle coordinates already here. Now let me write this out. So this is I times the sum over j equals 2 to L LPJ times RJ1. Right? Because our previous coordinates were coordinates relative to particle 1. So they are all RJ1s here. All right. And then I have plus I times the sum over A larger B over all these contributions here. KAB prime times RAB minus RA1 plus RB1. And now we are done. And now you see that I can suitably combine these wave vectors. And of course, I need to integrate over all my new wave vectors here. Okay, Now let me write this in the following way. I'm introducing a new set of wave vectors kjk, one for each of the relative particle distances here. And now the kjk, of course, have a meaning, and I can construct them. I can construct them from what is above. All right. So what do these kjk's now mean? Now I need to distinguish the case k equals 1 from k equals something else. If k is 1, I need to combine these LPs, these LQs here, with these contributions that also have the second particle index 1. And if k is different from 1, I can just use the primed wave vector. If k is 1, then I need to take the sum from j equals 2 to L over L qj minus sum always doing this wrong. J equals b plus 1 to L kjd prime plus the sum from j equals 1 2 to L minus 1 ka j prime. This is for j equals 1. This combines this with this contribution and takes into account that this is a double sum here. A sum over all b from 2 to L minus 1, and then a sum from b plus 1 to L. And this is why once we have the sum over all contributions from the first index with a negative sign and add all contributions from the second index with a positive sign. And this, well, if j is 1, that's the case, k equals 1, yes. That's true. And then, of course, yeah, this is why this runs from 2 to L, for example, and this runs from 2 to L. All right. And this is for k equals 2, and then, of course, j is 3 to L. All right. This looks like an awkward scheme, but suppose you have L equals 3, just as an example, right? Then you have K2, 1. Now here we would have to take the sum from 2 to 3. So this is LQ2 plus LQ3. Then we would have K is 2. So this is now minus sum from 2 to 3. But then B must be 1. So this is minus no, sorry. See, I'm confusing myself here. B must at least be 2. Right? We said before that B is enumerating wave vectors from 2 upward. So the smallest number for B that we have is 2. And then K must run from 3 to 3. So we have minus K32 prime. What else did I do wrong? Okay. Huh? It's meant to be like this. Uh-huh. I realize this now, yes. Okay. Look it up in the script. You see the principle, right? The principle is that we can introduce new wave vectors such that a small set of them contains the shift vectors, and we need to introduce new wave vectors like this. But now, for each pair of J and K, we get an individual exponential factor. And we have one contribution that contains all equal indices. This goes out front and is gone. But then we have LPJs, CPJ, BKs, LPKs. And we have these vectors here. So then we get exponential factors for each pair of J and K, which are all independent. So this means that I can write this as some normalization factor, an integral over all new wave vectors KAB prime, an integral over all particle coordinate pairs, and now a generic factor IJK. All right, and you know this factor already. Let's wipe this off. This is it's going to be right in the lecture notes, but the principle is the important thing. So this is now going to be a function of, now what are the independent variables? I'm integrating over the radius here, over the distance. So this is not independent anymore. The only quantities that I have are LPJ, LPK, and the wave vector. So I can introduce a new function I of, let's say, some vector L1, which is just a three-dimensional vector now, some vector L2, and some wave vector K, and this is the integral over the radius exponential of minus a half L1 transpose CPP L2 plus I times K times R. And these are three-dimensional vectors. And you know what this is, right? This is just our curly P, essentially. Right? So this is a 2 pi cubed delta a delta of K. If I split off like before, minus 1 from this exponential here, plus a curly P depending on L1, L2, and K. So now we have split up our free generating functional into individual standardized factors. And this is very important, in particular when we will introduce particle interactions. So this means that at the end, all these factors here are decomposed into a Fourier 1, so 1 plus a curly P. And then you take products of these. Wait a moment. These integrals are gone. And they are all products of these factors here. So this allows us then to set up a hierarchy of products between curly P's here. First of all, this means that once you know what these nonlinear free power spectra are, you can produce the free generating functional just as a product. And you will have to integrate the new wave vectors. The factors are just Fourier 1s times plus curly P. So all these products are 1 plus terms of first order in P times terms of second order in P times third order in P. Okay? Yeah. Honestly, I don't know. I don't know if you can call this a gauge transformation. But this makes me I'm stumbling. I'm stumbling over the gauge. Over the new basis. What do you call the new base? The new coordinate differences here. This can't be a base transformation because we have so many more than original coordinates. unless you expand your space into L times L minus 1 divided by 2 dimensions. That's an extremely interesting point. Tell me more about this, Louis. In some quiet moment. That's very interesting. I mean, you see, what I'm now driving at is just this factorization here. But if there is an easier and more systematic way to arrive there, I would, of course, be very grateful, as you've noticed. The result is correct, but the way there could be very much simplified. Aha. Well, let's talk about this. I mean, what I will later need as we go along when we introduce particle interactions is exactly that we can write the free generating function as a product like this, and that we can then order terms by order of power spectra that enter into them, and so on and so forth. And so there's a very convenient ordering scheme that arises there, and many other things, as you know. But let's stop it at this point. Now, today is December 8th. So next Thursday is December 15. The one after that is December 22, and this is already in the Christmas break. So next time is the last time before Christmas. And then we are doing particle interactions and things like that. And then you can take a rest. All right. See you next Thursday then. Okay, du wirst dann da dem Hannes begegnen wahrscheinlich. Ja. Weil ich euch beide in dieselbe Stunde quetschen muss. Aber ich denke, wir schaffen das. Ne? Für den ich gefragt habe, ist sowieso, ja. Ist am 21. Tutorium? Ja. Okay. Das war die Frage, die kam gestern im Tutorium auf. Ja, weil die Winterpause offiziell erst am 22. anfängt. Okay. Und dann können wir nicht einfach am 21. schon aufhören. Ja, ja. Okay. You already raised it, but why we only consider here two cases when k equals 1 and k equals 2 only? Because we only have the contribution from the LQs if we refer to particles relative to particle 1. Right? This is from the original Fourier phase. This comes from the LQ times R. But the old R's are RJ1s. And this is why we have this contribution of the L's only for k equals 1. But this is for k equals 2? 2 and higher. Higher, right? Okay. So larger or equal to. Wann möchten Sie denn anfangen? Ab April oder sowas? Das geht. Also vorher. Vorher schwierig. Vorher hätte ich keinen Platz. Ab April geht, ja. Kommen Sie doch mal in meine Sprechstunde. Dann sprechen wir über mögliche Themen und wie es losgehen könnte oder so. Aber das hat noch Zeit. Ne? Wie ist Ihr Name? Wie ist Ihr Name? Taxis? Von Taxis? Okay. Ah ja, okay. Dann sehe ich Sie fest vor ab April. Und wir würden dann ein konkretes Thema besprechen, wenn die Zeit da ist. Ne? Okay, soll ich dann nach Weihnachten sprechen? Am besten, ja. Irgendwann im Laufe des Januar oder sowas. Ne? Sprechen wir darüber und ich gebe ihm was zu lesen und sowas. Hello, you made it. Huh?
I was in the interview with you for my master's program. The interview for my master's.
Really?
Yeah. I said I'd be meeting you sure once I get there.
Oh, great. Great. You see, it's difficult to recognize people again if you only see them on the screen. So it's a real pleasure to see you here. Hello.
So yes,
Hello, welcome here.
I came in like a month and a half late because of my visa.
I have heard that essentially all people from India and China also had enormous problems with the visa. So what's your situation now?
Now, so basically, I thought I could take experimental particle physics, but like I did sit in the class, and my bachelor's education doesn't really go well with it. I would need to work a lot more.
Okay.
So
Yeah.
I did take physics classes today for experimental particle
Mm.
astrophysics.
Mm.
I did sit in the class. I was able to understand it a bit, but I do need to do a lot of background. So what I'm planning to do is take astrophysics and cosmology as subjects for this.
All right. All right.
I just wanted to have a discussion with you, like how I can approach the subject and what all the work I'm supposed to do.
All right.
I mean, my bachelor's is in mathematics, physics, and chemistry. It's a triple major, but like because it's such a constrained thing, they had to like cut down a lot of things. I didn't have much choice.
Mm.
Right now, like getting to that point where I'll be able to understand completely is a little bit difficult. But I'm sure I can sit down properly, go through the textbooks,
Mm.
I
Mm.
can catch up.
All right. So you're now having the cosmology class, astrophysics.
Yes.
So theoretical astrophysics with Matteo Maturi.
Yes.
All right. And particle physics.
Oh no, particle physics.
No particle physics. Okay. Okay. Now, first of all, I think that Matteo Maturi is following the course that I have designed.
Yes. Your textbook has.
Okay, so you do have this textbook. Okay, fine. This is what I would have recommended to you. And then, who is giving the cosmology classes? Luca Amendola.
Yes.
All right. What kind of material does he have?
I did see a textbook, but he said that he has shared his Dropbox link with me, and there is a lot of written material on this, all the slides. I still have to go through it. I'll be.
If you go on my webpage, you find lecture notes for a cosmology course that I've given, and for a course that was called Observing the Big Bang. And I think Luca Amendola is combining essentially both of them. So if you want written material, you find it there as well.
In your webpage?
On my webpage, there's a section called previous lectures,
yes.
And then you find the lecture notes.
I also have that I didn't still get my enrollment ID because universities are upgrading to a different system. So they're like, maybe it might take a week more to get my student. So I'm unable to like enter the practical groups, the practice group and everything properly, but I'm just emailing it.
Okay, that's fine. That's fine. I mean, they can enter you by hand all the time. I mean, it's really unfortunate that your visa got delayed, and this also puts a lot of a huge burden on you to catch up with things.
But I mean, it is fine. We are like completely used to kind of present back in it.
Okay.
It's too much syllabus.
Yeah.
So I think I'll be able to.
All right. All right.
I mean, if I'm unable to like finish everything properly by the semester due, like in 4 semesters, so I'm completely okay with taking another semester.
Yeah. All right.
Because I do even have a plan to like do a PhD as well.
Yeah.
So the more knowledge I can gain properly, the better.
All right.
Because I'm completely sure that my bachelor's degree taught me nothing compared to standards that are today. So I need to do a lot.
Well, I think it's important if you identify what the real gaps are, and see that you can fill them in.
Exactly. That's
And this is essentially what this theoretical astrophysics book was planned for, right? To build upon material that
was missing the
most readers should be available. Should be available. Right. But in order to access, for example, these lecture notes or the lecture notes in cosmology that I have, you don't need a university ID. They're completely open.
I will go through it. I did find the textbook, the new textbook.
Yeah.
I used to have the old textbook. I did buy the physical book back in India.
That was ridiculously expensive. This is why I got it. Why I tried to get it back from the publisher, which was Wiley at the time.
Yeah.
And they gave it back to me because they didn't sell any copies. And then I republished this in Heidelberg University Publishing, and this means that it's free now.
It's a good book. I mean, I got it when I was in my 9th grade or 10th grade. I was going to a bookshop and I found introduction to theory. That I'm interested in. I didn't understand a word of it back then, but with time when I was doing 11th grade, 12th grade, I was able to catch up with the things.
All right, lovely. Okay.
So I will try to go through your lecture notes and there are other ones as well. I'll try to fully catch up with all of those.
Yeah. And if you encounter any trouble, let me know, or pass by my office hour or so.
So Tuesday you're available.
Tuesdays 4 to 5. Yeah. All right.
I mean, the transportation system is really good compared to India. But like I'm still trying to get used to the timings and everything.
Yeah. On the other hand, most of the time you don't need it if you go around in the old part of town, just because Heidelberg is so small. I'm usually going around with a bike.
Oh, I'm trying to get a bike.
Yeah.
I'm staying over in Leiden.
Ah, okay. Okay, then you need the tram. Yeah. All right. Good to meet you too.
And I'll drop by again.
Yeah, you're most welcome. Most welcome to pass by. All right.
As I told you during the interview, like you and Professor Kanpur, you're like the celebrities. So it's really nice.
Well, of course, that's very flattering for us. All right, it's great to see you here.
I'll see you soon.
All right.
Have a lovely evening.
You too. Thank you. Sterne und Weltraum? Soll ich das machen, ja? Soll ich morgen mal mit dem Chefredakteur reden?
Ja, das wäre
Keine Ursache. Das ist im Moment die einzige Verbindung, die ich noch zu Springer Nature habe. Also über Sterne und Weltraum. Also ich versuche es mal da. Es gibt noch einen anderen Weg über Physik in unserer Zeit. Also das ist auch eine Zeitschrift, die allerdings für Lehrer gedacht ist, Physiklehrer. Und da habe ich auch Kontakt zu dem Redakteur. Das heißt, wenn es mit Sterne und Weltraum nicht klappt, dann versuche ich es dort. Ne?
Okay, ja.
Aber ich versuche es erstmal morgen mit dem Andreas Müller, dem Chefredakteur von Sterne und Weltraum. Und dann schauen wir. Hallo. Ja. Die Klausur hier?
Ja. Weil ich dann bestimmte Themen zum Beispiel gedacht habe, dass es rausgesetzt wird. Irgendwelche Sachen, die ich finden sollte.
Also einen großen Teil davon kannst du ja schon. Also ich denke, wir werden es so machen wie bei den anderen Vorlesungen, dass die Klausur auf den Übungsblättern aufbaut. Und das heißt, wenn du die schaffst, dann schaffst du die Klausur auch. Das schaffst du auf jeden Fall. Ja, genauso wie Bachelor-Klausur. Also wir üben die Sachen ein mit Übungsblättern und bauen die Klausur auf den Übungsblättern auf. Es hat geklappt. Wunderbar. Wunderbar. Arizona war das bei dir, ne? Genau. Ja. Ah, wunderbar.
Ja.
Schön zu hören.
Auf jeden Fall.
Sehr gerne. Sehr gerne. Ist immer schön zu hören, dass die Dinge tatsächlich was bewirken. Ich glaube, so viele wie in diesem Herbst habe ich noch nie geschrieben, seitdem ich in Heidelberg bin.
So viel Vorstellungsgespräche, die alle wollten, aber
Genau. Naja, schön zu hören, das hilft. Prima. Und das heißt, du würdest dann im nächsten Jahr dahin gehen. Also in einem Jahr jetzt.
dann die Arizona State University auch noch die
Ah, okay. Aha. Gut, okay. Wenn du für irgendwas nochmal einen Brief brauchst, dann sag Bescheid.
Vielen Dank.
Gerne. Gut. Tschüss. Hallo.